I can fight monsters, I can't fight physics.
Hello, Ziad. So this question's a young modulus question. So if lengths of a rail track are laid down in cold weather, they may deform as they expand, so they'll stretch when they get heated, when the weather becomes warmer. Okay, so therefore, when rails are laid in cold weather, they are stretched and fixed into place while still stretched. Okay, so this is called pre-straining, so stretching it before they're putting it in. Okay, so the following data is typical for a length of steel rail, so young modulus, cross-sectional area, and the amount of pre-strain. So this is the sort of new bit that you don't get on all sorts of typical young modulus questions. So the amount of pre-strain is 2.5 times 10 to the minus 5 for each Kelvin rise in temperature. The rail is expected to rise. So that's saying if it goes up by 1 degree Celsius, you expect an extra pre-strain of 2.5 times 10 to the minus 5. So if it goes up, let's say, for example, the pre-strain was 5 times 10 to the minus 5, that means you're expecting a 2 degree rise. Okay, so it's 2.5 times 10 to the minus 5 for each degree rise. So if you look at a steel rail is laid when the temperature is 8 degrees Celsius, so that's not really warm at all, maybe it's a cold country, and the engineer decides to use a pre-strain of 3 times 10 to the minus 4. So 3 times 10 to the minus 4, and if you divide that by 2.5 times 10 to the minus 5, that will tell you how many degrees that engineer is expecting that the temperature to rise by. So if you do that, that is equal to 12. Okay, so that is so they're expecting, so it's 12 degrees Kelvin, which is the same as 12 degrees Celsius. So they're expecting the max temperature to be 12 on top of the 8, so it's 20 degrees Celsius. Okay, so that's what that means. So maybe we're going to use that later on. So let's have a look. So calculate the tensile force required to produce the pre-strain in the rail required by the engineers. So they've told you the pre-strain, and we've also got the young modulus. So we've got to work out force, and the only formula with force is stress is equal to F over A, and they give you the A. So you got A, you got the young modulus, okay, and they've given you the total pre-strain. So what do we know? Well, you just write your formula down. Young modulus is stress over strain. Okay, so therefore stress is equal to the Young modulus times strain. Okay, so that is 2 times 10 to the 11 times a strain, total strain of 3 times 10 to the minus 4. So if you put that into your calculator, so that'll give you 6 times 10 to the 7 pascals. So that's your stress. Now, what do we know? Stress is force over area. So force is stress times area, which is a stress of 6 times 10 to the 7 multiplied by 7.5 times 10 to the minus 3. So if you put all that in, so that will give you 4.5 times 10 to the 5 newtons. Okay, so you just, with most of the modulus questions, they're not very conceptual. They just punch all the numbers in. Maybe that stuff in the purple ink. So calculate the elastic strain energy stored in a rail of unstressed length 45 meters. Okay, so strain energy, what do we know? Strain energy is equal to a half K extension squared. I'll just use E for extension, or you could use energy is equal to a half FE. Now we haven't got a spring constant, but we've just worked out the force. Okay, so maybe we could do it that way. So right, so first of all, we've got to work out the extension. We've got the length here, 45. We need the extension. So we could use strain. is equal to extension, I'll use E this time, E over L. So therefore the extension is strain times length. So that is equal to the pre-strain is 3 times 10 to the minus 4 times 45. So there's my extension, which is 0.0135 meters. And then I can put that into E equals a half FE. So half times 4.5 times 10 to the 5 times by that extension, which is 0.0135. So that gives you 3038. Okay, so again, elastic strain energy. Look at the formulas you got, look at what you can work out, and it's usually the case. Calculate the temperature, which the steel rail becomes unstressed. So I think we just worked that out. So that was at 20 degrees from earlier. 20 degrees from earlier. So that's where that pre-strain information is useful. Okay. But like otherwise, it's not something you'd be expected to know about. So explain why engineers does not use the highest observed temperature. I presume 20 degrees is peak summer for them, so it's not always that hot. So track is not always that hot. Always at 20 degrees Celsius. So you want to limit the time spent under maximum stress. Okay,